Hi, we are Team Simbot from the Navigation and Interaction track. I'm Jessica. Today with my teammate Dakshaja, Kushagra, Malaika, Sai, and Venice, we're going to present the work we've done for this semester. So we work on embodied task completion, and more specifically, we focus on vision and language task completion based on egocentric visual observations and natural language instructions. So our project has three main parts: scene understanding, navigation and object interaction, and dialogue part where the agent can ask questions and interact with the commander. So the use case we have a wide range of use case for our project. Firstly, our bot could be used as a household assistive bot where it can perform regular day-to-day activities and assist people with disabilities. Our bot can also be used to navigate towards hard-to-reach places in search and rescue scenario. It can be applied to game development as well, where there will be an interactive game on Amazon's Alexa Simbot Challenge platform, where human users will provide instructions to complete tasks. So throughout our project, we mainly played with two data sets, Alpha and Teach. Alpha stands for Action Learning from Realistic Environments and Directives. It is a data set for embodied task completion. It maps egocentric RGB image frames and natural language instructions to actions. However, one limitation is that it does not allow for dialogue. That means the agent cannot ask clarifying questions when it gets stuck with the task. So that might lead to potential failures. On the other hand, the Teach dataset stands for Task-Driven Embodied Agent.chat. It includes over 3,000 dialogues between the commander and the follower. So here, commander has all the oracle information about the task, and the follower navigates and interacts with environment to complete the task. So follower can ask questions to get additional information from the commander when it cannot proceed with the task, and it will lead to a higher task completion success rate.
So our work builds on top of Film, which is a modular system for embodied task completion. Film is composed of three main components, the first of which is a language parser, which is responsible for parsing natural language instructions into a semantic form that the rest of the system can understand. The next component is a semantic mapping component, which is responsible for identifying and localizing objects in the environment. And finally, there is a navigation and object interaction module, which is responsible for generating a sequence of actions that the agent must execute given the instruction and the map of the environment. So let's dive a little deeper into our system architecture. The first component is the language parser, which is responsible for identifying the type of the task, as well as the objects that the agent must interact with to complete the task. Specifically, it is composed of two BERT models. The first BERT model is responsible for identifying the task type, and the second BERT model is responsible for identifying the arguments of the task or the objects to be interacted with to complete the task. So for example, in this instruction, drop a clean pan on the table. The first BERT model identifies the type of the task as a clean and place task, while the argument classification BERT model identifies that it must interact with the pan and it must place the pan on a receptacle object, which is the table. Given the task type and the task arguments, subtask templates are populated, which are then used as input to the navigation and interaction action generator at a later stage in the pipeline. The next component is the semantic map generator, which is responsible for understanding RGB egocentric views observed by the agent. This is again composed of two modules, an instance segmentation module, which is responsible for identifying objects and localizing them within the scene, and a depth estimation module, which is responsible for identifying the relative position of objects with respect to the agent's current position in the scene. So this visual is an example of how semantic maps are constructed. On the left, you can see the RGB view of the agent. The tile in the middle shows you the segmented RGB view of the agent. So you can see object types and masks over identified objects in the scene. And this segmented output is combined with the depth estimates to come up with a two-dimensional semantic map that you see on the right that gets iteratively updated as the agent moves through the scene. The next component is the semantic search component, or a sub-goal object localizer. So some objects might be harder to find in the scene than others. This could be because of their small size, or they are occluded or hidden away inside receptacles. The goal of the semantic search module is to approximate the location of these harder to find objects, given the maps of given the locations of the larger and more easy to find objects. The final component is the navigation and interaction module, which is responsible for generating a sequence of either navigation or interaction actions that the agent must execute to either move towards an object it must interact with or actually execute an interaction action. And finally, we also have a clarification generator, which is responsible or which enables the agent to identify when it needs help or when it needs more information to accomplish a task, as well as what information to pass on to a dialogue generator to construct a question to get the information it needs to successfully complete the task.
Over the last semester, we faced and solved a lot of engineering challenges. The most important ones are listed on the slide. So first of all, we had to port film code from the older version of Air to Thor to the latest version. After that, we applied film from the Alfred dataset to the Teach dataset, whose APIs are quite different, and it was a lot of effort. After that, we did an extensive dataset research and came up with new task templates for the Teach dataset. Since we are trying to participate in the Alexa Prize Simbot challenge, we had to set up a full submission pipeline, which included Docker and Kubernetes, and we had to set up an infrastructure to run film on Teach. Right now, we have made a baseline submission to the challenge. As you can see, it's called TartanBot. We would try to improve upon this solution over the next semester. Now let's just have a brief look at the flow within the navigation module. As Malaika explained, we have the following high-level components. The commander issues high-level instructions to the language parser, which converts it into low-level subtasks. The follower consumes the low-level subtasks as well as egocentric RGB images to construct its version of the semantic map of the environment. This semantic map is updated with each iteration that the follower takes. Finally, the updated semantic map, along with the predicted subtask, subtask goal, as well as the goal location, is taken by the navigation and interaction action generator, and the final action that the follower is supposed to take is generated. And this process continues over time. Finally, we take a brief look at our evaluation metrics. First of all, we have success rate, which is a binary indicator of whether all the subtasks in the full task were completed. We also have goal condition success, which is the ratio of successfully completed goal conditions at the end of an episode. We also have path weighted metrics, which consider how long the agent took to complete a given task as extra metrics.
Yeah, so now I will introduce some of the challenges that we have identified in our project and the hypothesis, as well as the proposed solutions. So the first challenge we have faced is processing low-level actions. So our current film model have some failures in locating the sub-goal object, and the failures are mainly due to several reasons. The first one is goal object not found. That means the objects being too small and not visible from the current frame. There could also be some interaction failures. That means the object being too far or not in the field of view. There could also be some collision during the process of navigation, or the object is in a closed receptacle. And finally, there could be language processing error. That means we incorrectly process the language instructions. So for now, we'll just focus on the force arrow mode, which is object is in closed receptacle. For example, if the object that we want to pick up is in the cabinet or a drawer, etc., then we might not have the access to the object. So the proposed solution is to convert those low-level details into action sequences. And let's dig into more details. So there are 7 goal types in the film model, and we have design templates for each of the goals. So if let's say the language instruction is hit an apple and put the apple on the counter, then it will be categorized into this type: pick, hit, then place in receptacle. So what we need to do to successfully complete the instruction is to pick up the apple, which is the object target here, and then put the apple in the microwave, toggle on and off the microwave, pick up the apple from the microwave, and put the apple on the counter, which is the parent target here. And in order to put the apple in the microwave, we need to open and close the microwave. And in order to pick up the apple from the microwave, we need to open and close the microwave. So that's our current solution in film. Like that's the template that we designed for this goal type. And opening and closing the microwave are already being added around those actions because they are semantically entailed with the task, with this heating task. However, we missed the fact that this object target, it could be originated from like a closed receptacle, so we can't access the object. So our proposed solution is to first identify the closed receptacle and add the opening and closing receptacle action pair around this pickup action. So we further investigated the validation data set to see out of the 821 instructions, how many instructions have this kind of problem of the object enclosed receptacle. And the most two frequent cases, as you can see, is in the fridge and in the microwave. And they are already being dealt with because they are semantically entailed with the heating task and cooling task. However, there are many other cases that are not semantically entailed with the goal. And then, for example, in a drawer, in a cabinet, in the refrigerator, into the bin, in the trash can, and they are also relatively frequent. So we have to deal with them, and that's where we plan to work on in the next semester to complete the task template by adding more action sequences.
So next we explore the different granularities in the search space cells in a semantic map. So this problem is important because semantic map is crucial to localizing objects in a scene, and the granularity of the search space cells determines the accuracy to which the individual objects can be localized. Small granularities, they help in localizing the smaller objects in crowded scenes, such as objects on the kitchen countertop or those on top of a study table. Larger granularities, on the other hand, they help in reducing the computational complexity of the search operation, and they are ideal for areas where small objects are not expected, such as floors. Larger granularities, they, however, prevent isolating smaller objects in cluttered surroundings. Thus, our proposed solution is to strike an appropriate balance between the fine-grained and the coarse-grained map granularities, and to arrive at an optimal dynamic map granularity policy for the different regions of the scene. So if we look at figure A, for example, it provides an instance of large granularity. We see that three different objects, that is a plate, a spoon, and a spectacle, they're all present in the same search space cell. The agent in such a case finds it difficult to isolate these individual objects from which are present in the same search space cell. Figure B shows an example of an extremely fine-grained granularity, wherein each search space cell contains only a single object, but each object spans many different search space cells. This makes it difficult for the agent to isolate the entire object out of the many different cells in which it is present. So we strike a balance between the large granularity in A and the small granularity in B to arrive at an optimal granularity level in figure C, wherein each search space cell contains a single object and an object does not span too many different search space cells. So to validate our hypothesis, we conducted a preliminary experiment wherein we took 120 test tasks. So each task can be something like move the spatula from the counter to the sink, or to put a clean bar of soap in the tub. So for the 5x5 granularity, we obtained the maximum number of successes, that is 31 out of the 120, while the number was lower for 4x4 and 6x6 levels of granularity. And our hypothesis is that this is because currently the semantic maps are trained on 5x5 granularity cells. We expect that by modifying training to incorporate other levels of granularity, we'll be able to improve on this performance, particularly for cluttered regions where objects are close by and smaller granularities should intuitively work well. So in the following semester, we'll be beginning with training the semantic maps for smaller granularities like 3x3 and 4x4. We'll then be experimenting with dynamic granularity policies for different regions of a particular scene. And ultimately, we expect these granularities to be learned for the various regions, depending on the object size and the level of clutter that is generally seen in those regions.
The next challenge that we would discuss pertains to the depth estimation model. So as you can see, inaccurate depth estimation models can lead to errors in both interaction and navigation scenarios. From the table, it is clear that when the model is provided with ground truth depth instead of the predicted depth, both the goal completion and success rate metrics increase significantly, especially in the case of validation unseen split. So these failures can range between predicting inconsistent and non-smooth depths, also unable to recognize edges and corners, and also failure to accounting for small objects. The current fill architecture uses a unit model, which is a purely convolution-based approach. Here we show some of the results of the current unit model, where we show the egocentric RGB image, the ground truth depth, and also the predicted depth. In this particular example, you can see that the model completely fails to predict the chair in this particular example. And here the model is completely unaware of the edges between the wall and the floor. And finally, in one of the severe cases, the model is completely unaware of the table and is not able to predict the entire table itself. So in these particular cases, since the agent is unaware of these obstacles, it might lead into collisions. So one of the major factors for these failure cases can be owed to the fact that we use a purely convolutional depth estimation, so which cannot leverage any kind of global context. Also, it has an inherent bias to process all parts of the image in the same manner, irrespective of their absolute location. So what we propose is a transformer/sequence-based methods, which not only use local and global context, but also provide more smoother and more consistent depth estimations, also capture finer details, and also we try to incorporate some temporal information into our model. So we plan to try to use an attention-based model called transdepth. As you can see, this model performs a much better depth estimation. As you can see, it is able to identify all the rough surfaces, especially if you can see the glove in the image, it is able to predict it more accurately than compared to the unit model. Also, it is able to do a much better performance on all the smooth surfaces, like the sink in this particular example. Finally, we also try to approach this problem in a different perspective, where we try to incorporate some temporal information, like the proposed model here called many depth, which incorporates multiple frames as an input and tries to predict more granular and more accurate depth estimation.
To motivate the next iteration of our solution, I would like to ask you to look at the table of failures once again. So the major challenge right now in film is when the goal object is not found. And to understand how the bot actually tries to find these objects, we will have to look at the semantic mapping module. So the semantic mapping module takes in RGB egocentric views and depth estimates from the bot and tries to create an instant segmentation map. Further, this instant segmentation map is converted into a 2D representation of the entire space, which has binary outputs to suggest where each object is present. Right now, the current implementation of within film is that a deep convolutional network, almost a 15-layer deep convolutional network, is operated on the semantic map output to give a probability distribution. This probability distribution has very low granularity, and as you can see, it results in a very blurred output map. There are multiple reasons for the failure of film in this particular case. First of all, that many sub-goal objects within Alfred are very small and may not be captured during the actual semantic map generation. Some objects may be occluded within cabinets inside the fridge, or just the angle of viewing of the bot may be suboptimal to actually capture these. So to combine the probability distribution that we get from the convolutional map, we also try to use additional information in the form of lexical representations of both the receptacle as well as the sub-goal objects for better position determination. So the idea behind this is quite simple. We assume that similar objects would be found close by to each other. So taking an example, you would more likely find an apple on the dining table or the countertop or in the cabinet rather than in the bathtub or in the sink. So here is how our proposed solution looks. First of all, we divide the semantic map into search space cells, and we use the information, the binary information from the semantic map to understand which objects are present in each cell. We use BERT to create our object embeddings. So we do this pre-training because we have complete knowledge about all the receptacle as well as the other sub-goal objects that are part of the Alfred inventory or the Teach inventory. So we pre-compute the BERT embeddings from the objects. We get the corresponding embeddings which are present in the search space. We also have a query object, which in our case is the apple. We again do a lookup with our object embedding lookup table. We get embeddings for each of these, pass them through a similarity score function, and get scores. So the scores that we see right now, 0.87, 0.92, are similarity scores between the apple. We see, as an example, cabinet has a higher score. So we can estimate that these scores are good representations of how likely an object is present in that position. We apply a simple 2D softmax to get probabilities over the entire search space. We combine this with the convolutional probability to get hopefully a better representation, which has lower entropy and higher accurate location estimates.
The next major challenge that we have observed is that the ability of the agent to interact with an object is hindered when the agent has an incorrect orientation while trying to interact. So the current constraint in the setting is that an agent can interact with an object only if the object is within a 1 meter distance from the agent. And this scenario happens much more often than one would expect, because in each of the 12 high-level instructions, there are at least a minimum of 2 object interactions. And for the more complex tasks, such as prepare breakfast, there are at least 36 object interactions involved. And if the agent is unable to perform any one of these interactions correctly, then the entire task will result as a failure. And in the existing approach, the agent takes the shortest route in the direction of the object. So let's say we take the example given here, where the agent needs to pick up the sandwich, which is on the plate on the table on the other side of the table. Then the agent walks straight towards the plate, and it tries to pick it up, but it's on the other side of the table. It is not within the 1 meter range, so it is unable to pick it up. And the reorientation strategy that is currently in place is that if it's unable to interact, it rotates around in increments of 90 degrees and tries to repeats the action again. And you can see that such a strategy wouldn't work here, as the agent is rotating in the same place. So the proposed solution that we intend to implement over the next semester is to, firstly, we would be leveraging the fact that we are going to have much finer granularity over the semantic map. So we have much more precise locations of the sandwich and also the entire table. And second, we have a better depth estimation module as well. So first, we would leverage the depth estimation model to compute if the plate is from the tip of the table, if the plate is within a 1 meter range, and if so, we could take the shortest path. And if not, the agent learns that it has to take an alternate path. And secondly, it leverages the depth estimation module to detect all the obstacles and figure out which parts of the semantic map are traversable and which parts aren't. So once this has been figured out by the agent, we use the A* search algorithm with a direction of approach constraint to evaluate the optimal route that the agent can take. And in this case, we can see that such an algorithm will result in the agent taking the path around the faucet and approach the plate from the bottom such that it can interact with it.
So next we move to the deployment model. So currently both our data and models, they are deployed on Amazon EC2 instances. So these provide advantages, the most important one being lower cost since no additional hardware is involved. The next step is to deploy our model on the Amazon gamification platform to collect real-time data. And finally, our goal is to deploy the model on a fully functional robot, which is capable of carrying out action sequences. The major non-functional requirements include availability, which should be upwards of 99.9%, interoperability between the language module and the action and navigation module, and finally, security and data protection, which means that the actions must be ethically aligned and the data that Simbot uses should be properly protected. The major risks and challenges include product risks, wherein incorrect predictions and actions can lead to safety risks and damage to the robot itself. And the other important one is regulatory risk, which includes privacy concerns if the data is not properly handled and human safety is compromised. So moving to the resource requirements, the dataset that we use is the teach dataset, which has been discussed previously, and we make use of the AWS provided GPU compute. So these are the milestones for the current semester and for the following semester. references. And yeah, thank you so much. That's the end of our presentation, and we are open to any questions that you may have.
Great job, guys. So I certainly have some questions for you. Just give me a moment here. So the first question has to do with using BERT for recognizing the intent of the dialogue turn as well as the arguments, right? So that's something that's been studied and commercialized with Google Dialogflow. And the examples that you showed were pretty simple. So I guess I'm wondering why you're, not using a simpler, mechanism for recognizing the intents and the arguments. That's kind of I guess that's more of a, a reviewer type question if you were going to submit this, to a conference.
Short answer to that, we have based most of our solution based on what film is doing. So film, we have considered as our base solution. And at this point, most of our discussions or thought processes have been around this. And the challenges that we presented, we actually did not think about how we could change this, because we found that this was doing well enough that most of our problems or issues or the failure cases were not arising because of probably incorrect or
Okay.
BERT classification or BERT feature representations.
Okay, that's a good answer. But since you guys are in the business of trying to, get the best result on a leaderboard, sometimes the professor's vanity and ego have to suffer if their proposed approach is really like oversimplifying the problem, right? So you guys have exactly the right sort of rationality to fight these challenges with, which is, okay, if it works well enough, or it's not the big bottleneck, let's leave it the way it is and then focus on the areas where we can make the most impact. But don't be afraid to suggest to John and Yonatan that what film is doing right now oversimplifies the problem, because it could very well be that that's what's going on. My second comment is more general, and it really does strike at the heart of this architecture. So the first question I have is it possible in this data set to have a task that cannot be carried out, or all the tasks have a solution?
Does anyone want to take that? Or I could.
Yeah, currently all the tasks that are present in the TEAS dataset have can be successfully completed.
Great. So this is just like when the squad data set came out for neural question answering, where you never had to make a decision about whether or not the question was answerable or not, and you could just sort of fit a model to finding, the right answer. Okay. So let's say in the future, a new version of this data set comes out, and a large number of the tasks can't actually be carried out by the agent, and you actually lose points if you don't recognize immediately that the task can't be completed. So in fact, you lose points that are proportional to the amount of time that you try to solve the task before you declare that it's not solvable. Okay. Wow. So if we have a system like that, we're going to have to actually reason about what states are actually reachable, because you know how long the arm is. So you have to know whether you can get within a certain radius of the plate. And you might be able to do that very quickly and then say, hey, you know what, I can't go pick that plate up because it's too far in the middle of the counter and my arm's not long enough. Okay. So this leads me to my observation, which is you guys were basically talking about intermediate knowledge states of your system. Did I understand what the task is? Okay. Do I understand where the object is that I'm supposed to pick up? Maybe I don't. Maybe I can't find it, or maybe it's inside a container somewhere. But maybe I don't even know what container to look in. So what I have to really do is come back to the user and say, well, I can't even guess where the apple is. Can you tell me where it is? Okay. So you might want to consider a more explicit state space representation of your problem, where the system has to go through a sequence of knowledge states in order to complete the task solution. So it needs to understand what the task is. It needs to understand what objects are being discussed. It has to be able to navigate, to those objects and, carry out the required action. And personally, I would find it a lot more satisfying if you had a system that broke down what you're learning into those different steps in the sort of state space planning, paradigm. It's a very classic kind of a thing, because the real issue comes when you try to scale this up, and there's a chance for ambiguity or misunderstanding at every step of the way, right? So if I say, put the apple in the microwave, and in the past I managed to get apples out of the fridge and out of the cabinet, I can go search both of those places. So I can basically explore the possibilities to satisfy that first knowledge state of the location on my own. But if I have no idea what an apple looks like or where it might be in the kitchen, I have to ask the user. So have you guys talked about kind of making your architecture a little more explicit about the fact that there are different knowledge states? Because I think the way you guys are solving tasks, there's a sequential, set of knowledge states that you have to go through. And it just might be easier if you divide and conquer that way. Or is that outside the bounds of what you're expected to do with your architecture?
No, I think to answer your point, the teach dataset currently has 2 tasks, and we are focusing on just the first one. So the 2 tasks are execution from dialogue history. So you just have a sequence of dialogues between the commander and the follower, and commander would just probably be saying, okay, get the apple from the fridge, now put it in the microwave, now slice it up and give it to me. So
okay,
those are the high level instructions that the follower would take in, and that is all it gets. So it does not have the option to go back and say, oh, I did not find it in any of these places. I do not.
Oh, I see. So you don't have any interactive.
Exactly. So
dialogue.
that's the first part of the challenge. But the second part of the challenge that is getting opened up later towards this year, probably towards November, is a 2-agent task completion. So that's called TATC, I think. So in that case, the bot actually has the option to say, okay, I did not find it here, or I can't find it anywhere in the house. Where could I find it? And then the commander actually has an Oracle-like complete overview over the full environment, where he can say, okay, I'm sorry, there is no apple. You can't do this, or I don't want apples. Get me bread instead. But that, I think, is the latter stage of our project. And right now we are just focusing on the EDH, which is execution from dialogue history, because honestly, that is the first submission deadline we are faced with. So we are just focusing on that as of now.
Okay. Yeah, so I think then you should take my comments as kind of input for future work. And, I think I have some concerns about the generality of these tasks. If I really want to, sort of build an AI that can function in a variety of environments, I would be expecting, some interaction with the human. And I would be expecting there to be a lot of interaction about very ambiguous, instructions, given by the human, that have to be broken down into, different knowledge states. But yeah, so if the data set is set up to kind of swerve around those things, and you guys are just trying to do the best job that you can, then that's perfectly fine. And I understand that. But I would like to see something in your final report about whether you think this data set is really kind of realistic enough that it's going to give us a good embodied AI, or whether we need tougher data sets in the future.
I would just like to quickly mention that our team is mainly focusing on navigation and interaction. And the second part of the task, which has more dialogue management and interaction, we have another team which is actually working on that. And we would, in the next semester, we would actually work very closely with the other team as well to try and integrate both the solutions to make one as close as embodied AI agent that we can get. Yeah.
Okay, great. So Prasoon is making another point here in the chat, which is that clarifications and denials are actually going to be handled elsewhere. So that's fine. Okay. So I'll talk with those guys about that. That's fine. You also mentioned some sort of policy risks around, robots damaging themselves or the environment. but presumably your work is going on just in the cloud, right? So there's no possibility to actually damage anything, right? So do you have any requirements at all about safety, or was that just a throwaway to make people feel like you're not building, you know, killer robots or something?
No, I think that is the general a general concern with embodied AI. I think presently these things are not adopted in the real world, as in the real environments, but definitely when researchers devise algorithms, they try to put checks and balances regarding any such scenarios, and they put greater weight on that. That such situations should not arise.
Yeah, so I think you know, it's beyond the scope of your work, but probably in your final report, you should comment on what should be done in the future. Let's say if this was actually going to be put into a physical kitchen robot, you know, what would you have to change in order to you know, give a safety guarantee? And you know, John has just completed a PhD thesis on, you know, safe driving policies, where you're trying to jointly optimize a performance policy and a safety policy. And it crucially depends on having an actual representation of the current state of the agent and the sort of expected next state, you know, given an action that you want to invoke, because you have to decide whether it's safe, you know, to take that action or not. So that might also push you more into a world of, you know, having to do state space planning.
Yeah, sure. Yes.
Okay, any questions from Ashwin, John, Rana?
Yeah, I'm good as well, and we've hit the
Run
end.
out of time. Okay, thanks guys, great job.
Thanks.
Thank you, guys.